Newton never wrote F equals ma. What he wrote was that the change of motion is proportional to the force impressed. Motion for Newton meant momentum. Recover that reading and the second law becomes a statement about force acting over time. This chapter turns it into the most useful form of the law you will meet. Impulse equals change in momentum. Here is Newton's second law in his own words. The change of motion is proportional to the motive force impressed, and it happens along the straight line in which that force is applied. Two claims are packed into that sentence. First, proportionality. If a force generates some motion, doubling the force doubles the motion, and tripling it triples the motion, whether the force is applied all at once or gradually over time. Second, direction. The motion generated always points the same way as the force that generates it. Newton adds a third claim. Because the generated motion points along the force, it adds to or subtracts from any motion the body already had, depending on whether the two directions agree or oppose. And when they meet at an angle, the result is a new motion compounded from both. That is vector addition, stated long before vectors had a name. Momentum is a vector quantity, and it combines like one. Whenever you apply a force to an object by pushing it, pulling it, or hitting it, you apply that force over some discrete interval of time, delta t. During that interval, the force might stay constant, or it might vary in magnitude or direction. Some forces never stop acting at all, like the gravitational interaction between the Earth and the Moon. So this chapter investigates the relationship between forces and the time during which they act, and out of that come momentum, conservation of momentum, and a way to handle whole systems of particles. Consider a point-like object, a particle of mass m moving with velocity v relative to some fixed reference frame. The quantity of motion, the momentum p of that object, is defined as the product of its mass and its velocity. P equals mv. Momentum is a vector. Its direction is the direction of the velocity. Its magnitude is the mass times the instantaneous speed. And in the SI system, its units are kilogram meters per second, a combination that has no special name of its own. Momentum is reference frame dependent, and that is not a defect. It is a fact about motion itself. A ball rolling down the aisle of a moving train has one momentum as measured by a passenger, and a very different momentum as measured by someone standing on the platform. Neither measurement is wrong. Momentum only means something once you have named the frame you are measuring velocity in. Fix the frame first, and then P equals mv is unambiguous. Now suppose a non-uniform force F acts on the particle during a time interval delta t. We assume the mass of the point-like object does not change. Then Newton's second law reads, F equals mass times acceleration, which is mass times the derivative of velocity with respect to time. Because the mass is constant, it slides inside the derivative, giving the derivative of mass times velocity with respect to time. But mass times velocity is exactly the momentum. So the second law takes its compact form. F equals dp over dt. Force is the rate of change of momentum. Here is the new quantity. The impulse of a force acting on a particle during the time interval from t to t plus delta t is defined as the definite integral of the force over that interval. The impulse I equals the integral from t prime equals t to t prime equals t plus delta t of f of t prime dt prime. The prime variable is only the integration dummy, so the answer depends on the endpoints, not on it. And notice the units, Newton seconds, which unpack to kilogram meters per second. Those are exactly the units of momentum. Now apply Newton's second law inside that integral. The integrand f of t prime is the derivative dp over dt prime. So the impulse becomes the integral of dp over dt prime times dt prime, and the two differentials cancel. What is left is the integral of dp itself. taken from the momentum at time t to the momentum at time t plus delta t. Integrating a differential returns the quantity evaluated at the limits. So the impulse equals p at t plus delta t minus p at t. That difference is the change in momentum, delta p. Impulse equals change in momentum. This is Newton's second law in integral form. Read that result geometrically. Plot the force against time, and the impulse is the area under the curve between the two times. The detailed shape of the force history does not matter, only its area does. A large force acting briefly and a gentle force acting for a long time deliver the same change in momentum, provided they enclose the same area. That is the idea behind a crumple zone. Stretch the collision out in time, and the same change in momentum arrives through a much smaller force. One warning though, impulse is not a force. It carries momentum's units, kilogram meters per second, not newtons. The integral also lets us define an average. The average value of the force over the interval delta t is 1 over delta t times the integral of f of t prime dt prime taken across that interval. In words, total impulse divided by elapsed time. Geometrically, the average force is the height of the rectangle that has the same base, delta t, and the same area as the region under the actual force curve. It is the single constant force that would have done the same job. Multiply both sides of that definition by delta t. The product of the average force and the time interval over which it acts is called the average impulse. The average impulse equals the average force times delta t. And the right-hand side is now just the original integral, which we already showed equals delta p. So the average impulse applied to a particle during the interval also equals the change in momentum. Same physics, packaged for the common case where all you know is how hard something pushed on average. Let's put this to work. Take a total time interval delta t of 1 second. You push an object in the positive x direction. During the first half of the interval, from 0 to half a second, you push with a force that increases linearly with time. F of t equals b times t directed along the positive x-axis, with b equal to 20 newtons per second. During the second half, from half a second to 1 second, you push with a force that decreases linearly. F of t equals d minus b times t, with d equal to 20 newtons. The question is what impulse you apply to the object. Start by drawing the force versus time graph because the answer is going to be an area. At time 0, the force is 0. It climbs linearly, and at the midpoint, half a second, it reaches b times delta, t over 2, 20 newtons per second times half a second, which is 10 newtons. That is the peak. After the midpoint, the second expression takes over. At half a second, it gives 20 minus 20 times 1/2, also 10 newtons. So the two pieces agree at the joint and the force is continuous there. At 1 second, it gives 20 minus 20, which is 0. So the graph is a triangle, up from 0 to a peak of 10 newtons at the midpoint, then back down to 0 at 1 second. The impulse is the area under that curve. And this triangle splits into two right triangles, each with base delta t over 2 and height b delta t over 2. The area of each is 1/2 base times height, 1/2 times 10 newtons times half a second, which is 2.5 newton seconds. Two of them give 5 newton seconds. Written symbolically, the sum of the two triangles is 1/4 times b times delta t squared. Substitute the numbers. 1/4 times 20 newtons per second times 1 second squared gives 5 newton seconds, pointing in the positive x direction. And by the integral form of the second law, that 5 newton seconds is not merely an area, it is the object's change in momentum. Whatever the object's momentum was before you pushed, it is now larger by 5 kilogram meters per second in the positive x direction. Step back and look at the chain. Momentum, P equals mv, is Newton's quantity of motion. A vector tied to a reference frame measured in kilogram meters per second. Force is the rate at which momentum changes, F equals dp over dt. Integrate that over a time interval, and the differential form becomes the integral form. Impulse equals the change in momentum. Everything else followed from those two lines. Impulse is the area under a force versus time curve, and the average force is that area spread evenly across the interval. Carry this from one particle to many, and it becomes conservation of momentum. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.